So again, I want to welcome everyone to the program today. In this Superheat review, we're going to be going over Superheat and what it means to the evaporator coil. As we take a look at our first screen here, we see that we've got a basic refrigeration cycle, a graphic of a refrigeration cycle. And as we start out at the compressor, we're going to see we have a hot gas line going to an outdoor coil or a condenser coil. That condenser coil will then condense that hot gas into a liquid. It'll pass through a filter dryer and move down a liquid line where it's going to go to a metering device. Now that metering device, team, could be an expansion valve or TXV, or it could be a fixed orifice type of metering device. Anyway, the liquid refrigerant will go past that metering device and meter refrigerant into the indoor coil, which is going to be cold on an AC system and in the cooling mode on a heat pump system. That refrigerant will then boil off inside that cold coil and return on the suction line back to the compressor. Now, team, please note right in the middle of the screen you're going to have a suction gauge and a liquid pressure gauge. And very much like in the field, the suction is on the left and the liquid is on the right, just as if you were holding a manifold in your hand. In addition, we've also kind of color-coded those gauges. We've got a blue circle around the suction gauge, and we have a red circle around the liquid gauge. Now, another thing I'd like to point out is when we start to activate these gauges, if the background on the gauge is white, we automatically know this is an R22, an R22 service call. If it's pink or rose colored on the background, we'll automatically know that it's a 410A service call. So let's go ahead and jump into our Superheat review recorded session at this time. So the first thing I always like to do whenever we do a Superheat and subcooling session, I like to make sure everyone is familiar with the pressure temperature chart, also called a saturation temperature pressure temperature chart. So as you take a look at your pressure temperature chart, either your handout or if you have a generic pressure temperature chart, let's do some practice sessions together, because the foundation for Superheat is always finding the pressure temperature conversion is our very first step. So let's go ahead and find an R410A, find the R410A pressure temperature chart, and let's do some practice together. So starting out with our example at 55 psig, what is the pressure temperature conversion off of the chart for 55 psig or pounds of pressure? Good, exactly, 5 degrees Fahrenheit. Let's do another one at 130 psig for 410A. What is the pressure temperature conversion off of the chart? Good, excellent, about 45 degrees. Now remember, team, if your chart is showing you a decimal place after the whole numbers, in other words, if it's saying like 51.2 or 250.2 or 113.6, just round up or round down to the nearest digit. That's plenty close for field work. In addition, I want everybody to kind of start thinking along this line of thinking as well, that when you're taking a look at the pressure temperature chart, what you're really finding is the temperature conversion of that refrigerant inside that coil. Let me say it one more time. You're trying to find the temperature conversion of what's going on inside that coil. So to give an example, if I'm looking at the evaporator coil, and it's 130 psig in our example and 45 degrees, what that's really telling us is that refrigerant is changing state inside of that coil at that temperature. So in the evaporator coil, the liquid refrigerant that we sprayed past the metering device is actually boiling. In that example of 130 psi, it's actually boiling or changing state from a liquid to a vapor inside that evaporator coil. On the other hand, let's take a look at 265 psig, and we see that that's 87 87 degrees. At 265 pounds of pressure, that's 87 degrees. So if we were looking at a condenser coil or the warm coil sitting outside on the air conditioning system, and we had 265 psig discharge line pressure from the compressor, we would know that it was changing state at 87 degrees. So to put it another way, that hot gas is turning back into a liquid inside that condenser coil at 87 degrees. So when we take a look at the pressure temperature chart, team, I'd like everybody to kind of keep that in the back of their head, that what we're really looking for, we're looking for the temperature that the refrigerant is changing state inside the coil. So in the evaporator, we're changing liquid into a vapor as we absorb heat into that refrigerant from the airstream inside. And outside, we're rejecting heat off that hot gas in the condenser coil and turning that hot gas back into a liquid. Well, that happens at saturation temperature that we're looking at on our pressure temperature chart. So let's do another example. At 375 pounds of pressure for 410A, team, tell me at what temperature is that refrigerant turning back into a liquid inside the condenser coil? Good, that's right, at 112 degrees Fahrenheit. And our final example for 410A, at 455 pounds of pressure, at what temperature is that hot gas turning back into a liquid inside the condenser coil? Good, give yourself a star, 127 degrees Fahrenheit. So this time, you know, we've looked at some 410A examples. Now let's go ahead and take a look at some R22 examples, because we know there's still a lot of R22 equipment out there as well. So starting with our first example at 35 psig, at what temperature is that refrigerant changing state inside the evaporator coil? In other words, if I had 35 pounds of pressure on my suction gauge, at what temperature is that R22 boiling or changing state? At what temperature is that liquid refrigerant boiling or changing state inside that evaporator coil at 35 pounds of pressure? Good, that's correct, at 13 degrees. So if you had a way to look inside that coil, you'd actually see that at 13 degrees Fahrenheit, at 35 pounds of suction pressure, that those droplets of liquid refrigerant are actually boiling off into a cool vapor inside the evaporator. Let's do another one. At 68 pounds of pressure, at what temperature is that refrigerant changing state inside that evaporator? Good, that's correct, at 40 degrees. Let's do another one for R22. At 85 pounds of pressure, at what temperature is that refrigerant changing state inside that coil? Good, 51 degrees Fahrenheit. Give yourself a star. And just like we had before, at 230 pounds of pressure on the high side or the discharge side of the system, tell me at what temperature at 230 psig is that R22 hot gas refrigerant from the compressor turning back into a liquid inside the condenser coil? That is correct, at 111 degrees Fahrenheit. And one final example for our pressure temperature chart or pressure temperature conversion. Remember, team, we look at the pressure and we convert temperature. That's what this chart's all about. At 325 pounds of pressure for R22, tell me at what temperature is that refrigerant changing state inside that condenser coil? Good, that's correct, at 137 degrees. So team, this is step number 1 in finding superheat. And we'll learn later on in our next training module or recording module, and when it comes to subcooling on a condenser, it's also the first step to find subcooling. So you take pressure and convert it to temperature. That's step number 1. So when we do have superheat, it tells us the condition of our evaporator coil. It tells us the condition of the evaporator coil on a straight air conditioning system. It also tells us the condition of the cold coil on a heat pump. So superheat always applies to the cold coil. Whether that's a straight air conditioning system, or if it's a heat pump in the cooling mode, that would be the indoor coil. Or it could also be the heat pump in the heating mode, the outdoor coil. So remember, team, superheat always applies to the cold coil in an air conditioning or a heat pump system. Oh, and by the way, this goes hand in hand with commercial or residential equipment as well. Any evaporator coil, we're always going to be looking at superheat to find that condition of that coil. So one of the tools that we have for finding superheat on the indoor coil in the cooling mode on a heat pump or the indoor evaporator coil on a straight AC system is what we call a superheat chart. Now this superheat chart, I want to stress something, is only going to be used for a piston type of metering device on the indoor coil. Again, this is strictly for an orifice or a piston metering device. And so this is how we charge a system with a piston. If we have a system that has a piston or an orifice on the indoor coil, we have to charge that system by superheat. And if it happens to be a heat pump, we have to charge it by superheat in the cooling mode. Or if it's a straight AC system, we're going to charge by superheat if we have a piston on the indoor coil. Now please write this down or just make a mental note of this. If we have an expansion valve, also known as a TXV on the indoor coil, we're going to charge that system by a method called subcooling, which we'll discuss later. So subcooling is for expansion valves, and superheat is for pistons. Now it should be noted that superheat will always tell us the condition of that coil, and we'll get more into that in a little bit. But right now, let's just take a look at our superheat chart if we have a piston on the indoor coil and how we could use this chart to find the correct superheat. Please notice in the middle of this chart there are some diagonal lines. Those diagonal lines represent indoor return air temperature. Indoor return air temperature. You'll notice each diagonal line also has, on the left-hand side of the chart, you'll notice that it has a green block associated with that diagonal line. You'll notice those green blocks. An example, the very top one there says 95, 79. The next one down says 90, 75. The next one down says 85, 71, and so on. So those green blocks that are associated with the diagonal lines represent return air temperature, indoor return air temperature. Now please note that blue line, that blue number or that blue digits in those green blocks, that indicates dry bulb temperature. And the red digits or the red numbers indicate wet bulb temperature. So to give an example, again, our very top line there, 95, 79, that diagonal line represents 95 degree dry bulb return air temperature, but it also represents 79 degree wet bulb return air temperature. The next one down is 90 degree dry bulb, 75 degree wet bulb. The next one down is 85 degree dry bulb and 71 wet bulb, and so on. So just remember, team, that the blue numbers indicate dry bulb temperature and the red numbers indicate wet bulb temperature. So now the question arises, well, which one do I use? Well, that's a great question. So read in the text field at the very top of the chart, you'll see diagonal lines represent indoor return air temperature and dry bulb and wet bulb. Now read the next line down. If RH, or in other words, if relative humidity is above 70% or below 20% relative humidity, you have to use the red wet bulb line. If it's between 70% and 20%, let's say it's a 55% relative humidity, then you would use the dry bulb number. So this is important. We have to be able to measure our indoor return air temperature. We have to find wet bulb and dry bulb, and the way we're going to do that is we're going to use either a sling or a digital psychrometer, because we have to find wet bulb, dry bulb, and relative humidity, so we know which line to choose on those diagonal lines. Now at the very, very bottom of the chart, you're going to notice there's some numbers down there as well. Those numbers on the horizontal at the very bottom of the chart, that represents outdoor return air temperature. You'll please notice that outdoor temperature, not return temperature, but that outdoor temperature goes from 60 to 105 degrees Fahrenheit. That's outdoor temperature. You'll also notice on the left-hand side of the chart, the vertical numbers, the black vertical numbers, that represents the required superheat, at any given condition or measured condition. So again, the diagonal lines in the middle of the chart represent indoor return air temperature, wet bulb and dry bulb. The numbers at the very bottom of the chart represent outdoor temperature, and the numbers that go vertical on the left-hand side of the chart, those represent the required or the desired superheat under any point of measurement. So to use this chart, now remember, team, this chart's going to be used only for superheat charging with a piston on the indoor coil. You will not use this chart with a TXV or an expansion valve. This is strictly for piston charging only. So to find out what our superheat is supposed to be, we're going to take a look at the outdoor air temperature, step number 1. And so we're going to find the outdoor temperature at the bottom of the chart. So let's say in our example it's 90 degrees. We're then going to find the corresponding, we're going to measure our return air temperature. We're going to find the appropriate line that corresponds with our measured return air temperature, wet bulb or dry bulb, based on relative humidity. So in our example here, it looks like we're going to just use 80 degree dry bulb or 67 degree wet bulb based on your relative humidity. We find the appropriate line. And where those two lines intersect, the outdoor temperature line and the return air line, the diagonal return air line, where those two lines intersect, we move straight to the left and we find out what our superheat is supposed to be under those measurements, under the points of measurement. So in our example, if we had let's say we had 55% relative humidity and it's 80-degree dry bulb inside the space, we find that line. We measure it's 90 degrees outside. We move straight to the left and we find that our superheat, when the system's running, and we want to let that system run at least 10 or 15 minutes, team. We don't want to take this measurement right away. And a couple things too, you want to make sure you've got clean coils inside and outside. You want to make sure you have a clean air filter on the indoor unit. And you want to let the unit just run and stabilize for 10 or 15 minutes and just let it settle down before you do this measurement. And then after you let it settle down, about 10 or 15 minutes, you measure the superheat and see where it goes on this chart. And by the way, team, if it's within 1 or 2 degrees from the chart, just leave it alone. But let's give an example. Let's say, for instance, you're supposed to have 13 degrees of superheat in this example, and you've got 30 degrees of superheat. In other words, the superheat's high. Well, that means something. And so it's important that we use a chart to find out what our superheat is supposed to be. Likewise, if the superheat is only 5 degrees and it's supposed to be 13 and it's low, that means something else. And so we're going to be talking about superheat here shortly and what it means to the evaporator coil. But this chart will help us charge a system that's equipped with a piston or an orifice on the indoor coil. So this chart has to be used, or this type of chart has to be used, if you have a piston or an orifice on the indoor coil. So this time we also see that we have a blank chart. And if we do some examples together, we see, for instance, let's do an example. Let's say, for instance, we have 50% relative humidity. So we're going to be using the dry bulb line. So take your finger on the screen or take a look at your chart. And let's say it's 100 degrees outside. And maybe we're in Arizona or someplace where it's really hot. And so it's like 100 degrees outside. And we've got 40% relative humidity. It's pretty dry outside as well. And so 40% relative humidity in 100 degrees. And so in our example, let's say we have 85 degree dry bulb temperature, 40% relative humidity, 85 degree dry bulb temperature, that's that blue number. It's 100 degrees outside. If we find the intersection of that, we move straight to the left, we see we should have about 14 degrees of superheat in that example. Let's do one more and then we'll go ahead and talk about what superheat is. In this last example, let's say let's just say it's a warm and dry, or mild, a 95 degree day, semi-mild or semi-warm day. And let's say, for instance, it's pretty dry in the house. Again, let's say it's 50% relative humidity. But we find it's 95 degrees outside, 95 degrees outside. And we only have 75 degree return air temperature, 75 degree return air temperature. So take your 75 degree return air temperature, that's the blue number, 75 degrees, and intersect it with 95 and move straight to the left. What should our superheat be? Oh, that's right, team. Hang on a second. You never charge below 5 degrees. Now, if you get into a situation where, if you look and you say, well, gee whiz, that should be about 2 or 3 degrees. No. If you're ever charging or adjusting charge with a system with a piston on the indoor coil, never charge below 5 degrees, because if we do, we can flood the evaporator coil and flood liquid refrigerant back to the compressor, and that can damage the compressor. So this is really important. We did that on purpose in that example, because you may have 75 degree return air and it's 95 degrees outside. Well, and you may be tempted to say, well, I need to charge at 2 or 3 degrees. No, you never want to charge below 5 degrees of superheat when you're charging or adjusting charge, because you don't want to flood the compressor. Good. So if there's no serious comments about all that, of course, this is a recorded session, so I guess we wouldn't have comments, but just remember that, team. You never want to charge below 5 degrees of superheat on the superheat chart. Okay, at this time, let's talk about superheat and what it is. Superheat always tells us the condition of the evaporator coil. And so please write this down or make a note of this. If the superheat number is high, the evaporator is starved. There's not enough liquid refrigerant being metered into that evaporator coil. If the superheat is high, the evaporator is starved. If the superheat is low, the evaporator is flooded full of liquid refrigerant. Now, there's lots of reasons it could be flooded. That's the subject of another training session. We're not going to get into restricted liquid lines or oversized orifices or anything like that today. We're just going to be talking about what superheat is and how it applies to the evaporator coil. So if the superheat is high, the evaporator is starved. If the superheat is low, if the superheat number is low, the evaporator is flooded, and there's lots of reasons it could be flooded. Again, that's the subject of another training session. Step number 3 is the difference in the superheat level. So one of the things we want to make sure that when we calculate superheat, step number 1, we're going to convert suction pressure to temperature, just like we did in practice. Step number 2, we're going to measure the physical suction line temperature. Step number 3, we're going to find the difference, and the difference is our superheat level. Now remember, team, we're looking for the difference between suction pressure temperature conversion and the physical suction line temperature. The difference is your superheat level. And again, please write this down or remember this. If the superheat is high, that coil is starved of liquid. If the superheat is low, the coil is flooded full of liquid. If the superheat is running about, please write this down, about 10 to 15 degrees with an expansion valve, that will be considered normal. So 10 to 15 degrees with an expansion valve would be considered normal. Now remember, team, that's with an average line set of about 25 to 35 feet. About 10 to 15 degrees of superheat will tell you that that expansion valve is working properly. But as we learned in our previous slide or session, that the superheat is going to vary based on outdoor temperature and indoor return air temperature. With a piston, it's going to vary quite a bit. So if you have a piston on the indoor coil, you have to determine what the superheat is supposed to be off that chart and then compare it to what you actually measure to find out if it's high or low or normal. So again, a piston or an orifice, you'll have to look at the chart to find out what's supposed to be normal. But on an expansion valve or TXV, about 10 to 15 degrees of superheat will be considered normal if that valve is working properly. So one more time, to find superheat, we're going to, step number 1, convert suction pressure to temperature. Step number 2, we're going to measure the physical suction line temperature with a good high-quality temperature probe. Step number 3, we're going to find the difference, and the difference is our superheat level. And remember, team, if the superheat is high, a big number, the coil is starved. If the superheat is low, the coil is flooded. Okay, at this time, let's go ahead and take a look at let's do some superheat examples together. And in this particular example, you'll notice we're showing our refrigeration cycle, and we have 88 pounds of suction pressure. And please remember, too, if you have a white background, that means it's an R22 service call, R22 service call. If it has a pink or rose-colored background, we know that that's a 410A service call. Now, team, you're going to notice as you take a look at the refrigeration cycle, we have a hot gas line from the compressor going to the outdoor coil, going through a dryer and down a liquid line, through a metering device that could either be an orifice or a TXV. And that metering device is going to spray liquid refrigerant into the indoor coil where it's going to boil off into a vapor. That cool vapor will then return on a suction line back to the compressor. Now you'll notice that there's some arrows kind of pumping around to kind of show you the direction of refrigerant flow, just to kind of remind you and just to kind of stimulate your eyes a little bit to kind of see what we're doing. In addition, you're going to notice there's some yellow blocks. There's some yellow blocks located all around the refrigeration circuit. For instance, there's 2 yellow blocks across the dryer. We have not activated those because we're not looking at the liquid side of the system right now. We're strictly looking at the suction side. You'll notice that there's 2 temperature blocks along the liquid line. Again, we haven't activated those yet because we're not looking at liquid line temperature or across the dryer. We're looking at suction line temperature. And so when you're dealing with superheat, we want to look at that suction line temperature. And you're going to notice that we've got 2 temperature blocks that we have activated. In our example, we see we've got 54 degrees along that suction line. Now, team, you do what you want to do out there in the field, but I recommend that you take 2 temperatures whenever you're doing superheat. Take one at the evaporator coil, at the outlet of the evaporator coil, and outside just before it goes into the condenser on the suction line. Now, the reason I like you to do that is to make sure those temperatures are not significantly different. Now, sometimes what happens is that suction line goes through a real hot attic, and it can pick up some extra heat, or maybe that suction line's not real well insulated. So let's say we have 54 degrees at the outlet of the evaporator, but we've got 65 degrees at the inlet to the compressor. We're picking up 10 degrees of superheat, so that suction line needs to be insulated. As a matter of fact, team, we should never see any more than about 2 or 3 degree maximum temperature difference across that suction line, and if we do, we need to remediate that, because we want to make sure that suction line is well insulated and we don't pick up a lot of extra heat before it gets out to the compressor, because that can actually cause issues with the compressor not getting that cool gas back to the compressor. Because remember, team, it's the cool gas on the suction line that actually cools that compressor internally. So we want to make sure and have the proper superheat, but we don't want to have it too high as well. So again, we've activated the temperature blocks on the suction line. That's step number 2. So step number 1, we're going to take suction pressure off of our pressure temperature chart. We see that we've got an R22 system here. So if we take a look at our pressure temperature chart, we've got 88 pounds of pressure. 88 pounds of pressure. And so that's about 52 psi, 52 degree temperature at 88 pounds of pressure for R22. That's about 52 degrees. So step number 1, you take your suction pressure and convert it to temperature. We've got about 52 degree suction saturation temperature, and we've got 54 degree suction line temperature. So in this example, we've only got 2 degrees of superheat. So for whatever reason, we see that evaporator is very, very low superheat. And if we take a look at our superheat charging chart, we've got an orifice on this system. We see that we're never supposed to charge below 5 degrees of superheat off the chart with an orifice. But hang on, we've got 2 degrees of superheat. So in this example, we have very low superheat. That coil is flooded for whatever reason. Now, team, there's lots of reasons it could be flooded. We could have an oversized orifice. The piston might be too big, in other words, or it could be leaking. The system could be overcharged. There's lots of reasons we could have low superheat. That's the subject of another training session. But right now, we're just reviewing superheat and what it means to the evaporator or the cold coil on the system. So in this example, we have low superheat, a flooded coil. Let's do another one. Here we have an R410A system. We've got pink gauges. We have pink gauges, and that means it's an R410A system. We also are featuring an expansion valve or a TXV. Now remember, team, an expansion valve or a TXV should maintain, automatically, it should maintain about 10 to 15 degrees of superheat if that expansion valve is operating properly and it's working like it should. So let's do this example together. At 132 pounds of pressure, step number 1 on a 410A system at 132 pounds of pressure, we've got about 46 degree temperature pressure conversion, step number 1. Step number 2, we take the physical temperature of the suction line. We see it's 55 degrees in our example here on our temperature blocks. So the difference between 46 and 55 is about 9 degrees. Now, team, we're looking for about 10 to 15 degrees of superheat with that expansion valve. So our superheat's a little tiny bit low, but I'll tell you, if it's within 1 or 2 degrees of what you're looking for, consider that normal. What I would do in this case, I'd make sure that my coil was nice and clean inside, and I had a clean air filter on there and so on, and then put it back in service. But I would not start adjusting charge and all that kind of stuff with just a 1 degree deviation from the chart value. You could have that much deviation in the gauge itself, in your suction gauge. So in this example, we've got about 9 to 10 degrees of superheat. We would consider that about normal on this call. On the next one here, we see that we've got an orifice and 160 pounds of pressure. 160 pounds of pressure, it's a 410A unit. And so step number 1, at 160 pounds of pressure for 410A, we see that we've got about a 57 degree pressure temperature conversion at 160 pounds of pressure. Step number 1, if we convert 160 pounds of pressure 410A, we see we have about 57 degree pressure temperature conversion. And we notice that our suction line temperature is 58 degrees. And again, in this example, we only have about 1 degree of superheat. And even with an orifice, if we take a look at the chart, we're never supposed to charge below 5 degrees. And so in this example, we only have 1 degree of superheat, so we know that this coil is very, very flooded. We have very low superheat, so for whatever reason, we've got a flooded coil. And again, this is the subject of another diagnostic training. But you know, we could have an oversized orifice. We could have maybe somebody forgot to put the piston inside the orifice. Maybe it's just there's no orifice in there at all. Maybe they forgot to put the piston in. Maybe it's overcharged. There's lots of reasons you can have high suction pressure and low superheat, but those are just a couple to be thinking about. So in this example, we have an extremely flooded evaporator with low superheat. Here we've got an R22 system with a TXV. So again, team, with a TXV, we're looking for about 10 to 15 degrees of superheat under normal conditions, and we have an R22 system. We've got white background on the gauges. So let's take a look at the superheat on this and find out if that expansion valve is working pretty good or working pretty close to what it should be. So so step number 1, we take 82 pounds of suction pressure and convert it to temperature. We see that's about 59 degrees, about 59 degrees. And step number 2, we see our suction line is 68 degrees. So the difference between 49 and let me look at the chart here one more time. So it looks like we have 82 pounds of pressure. That's about 49. It's about 49 degrees. Pressure temperature conversion, step number 1. Step number 2, we've got 68 degrees on our suction line. So we have almost 20. We have about 19 to 20 degrees of superheat. Now remember, team, we're looking for about 10 to 15, but we have 20 degrees of superheat on this evaporator in this example. So our superheat is high. Our superheat is high in this example. What does that mean? That is correct. This coil is starved. It's starting to get starved for whatever reason. So for whatever reason, we're not feeding quite enough refrigerant into that evaporator coil under these conditions of temperature and outdoor temperature and so on. And so we'd have to find out why. You know, it could be something no more complicated than the fact that you know, the system is just under maybe a high heat load. Maybe it's just hot in the house with a 70-degree wet bulb inside. We see that we've got high suction pressure and high superheat in this example, and that coil, the indoor coil, is slightly starved with high superheat. Okay, in this example, we have another 410A system, 127 pounds of pressure. 127 pounds of pressure for 410A. So step number 1, we take 127 and convert it to temperature. And we see we've got about 44 degrees. And the suction line temperature is 53, so again, we're about 9 or 10 degrees superheat. So we consider this with an expansion valve, 10 degrees, 9 to 10 degrees. That would be within a normal range on that evaporator. Okay, so we talked a little bit earlier about, you know, a heat pump. A heat pump is going to have a cold coil. Now remember, team, that cold coil could be outside in the heating mode of operation, or it could be inside in the cooling mode of operation. So just please remember, superheat always applies to the cold coil on a heat pump. And we're using that word cold coil because we know that on a heat pump, depends on the mode of operation, that cold coil can be outside or inside based on the mode of operation. But team, please drill this into your brain. It doesn't matter if it's a straight air conditioning system. It doesn't matter if it's a heat pump in the heating mode. It doesn't matter if it's a heat pump in the cooling mode. Superheat always applies to the cold coil in the system. It always applies to the cold coil. And so the steps to find superheat do not change. Step number 1, you're still going to convert suction pressure to temperature. Step number 2, you're going to still measure suction line temperature, whether it's inside or outside, based on the mode of operation on a heat pump. Step number 3, you're going to find the difference, and the difference will be our superheat level. Now remember, team, if the superheat is high on any cold coil, if the superheat is high, that coil's starved. If the superheat is low, on any cold coil, that coil is flooded. Doesn't matter if it's on a heat pump or air conditioning system. If I have a low superheat, the coil is flooded. If I have high superheat on the cold coil, it's starved. So as we take a look at this, we see that again we've got R22 with a white background on the gauges. We've got some arrows pumping to kind of help us visualize which way the refrigerant's flowing. But now remember, team, on a heat pump we're going to have two expansion valves, one inside and one outside. Those are going to be biflow expansion valves. What I mean by that is in one direction they're going to meter refrigerant into the coil when that coil is acting like an evaporator or a cold coil. But hang on, when that coil is acting like a warm coil, that biflow TXV has a check valve circuit in it that's going to allow that liquid refrigerant to flow freely out of that warm coil when it's acting like a condenser or a warm coil. As we take a look at the basic refrigeration cycle, we see we've got hot gas coming from the compressor going to a reversing valve. And in the cooling mode of operation, that hot gas from the compressor will go to the outdoor coil, which is acting like a condenser in the cooling mode. That warm liquid will go through the biflow metering device outside, which is just a check valve circuit to let it flow freely in the cooling mode. It'll then go through a biflow filter dryer, down a common liquid line. And in this example, because we're in the cooling mode, that biflow TXV on the indoor coil is acting like an expansion valve, and it's spraying or metering refrigerant into the indoor coil, which is cold in the cooling mode on a heat pump. And then down that cool vapor line, we've got some temperature blocks. In our example, we've got 59 degrees. We've also given a temperature on the other cool line of the reversing valve back to the compressor, just as a point of reference. And when we're doing heat pump diagnostics, we need to be able to see the temperature across the two cool lines of the reversing valve. So we've activated those temperature blocks as well. We see in our example we do have an R22 system with 44 pounds of suction pressure in the cooling mode on a heat pump. Now remember, team, just because it's a heat pump, if we're in the cooling mode of operation, that indoor coil, if it's got an expansion valve on it, we're still looking for about 10 to 15 degrees of superheat for normal operation. And if that indoor coil happens to have a piston on it or an orifice, we can still use our superheat chart in the cooling mode on that heat pump if it's got a piston on the indoor coil. Now remember, team, the only time you're going to use the superheat chart on a heat pump is when you have the indoor coil with a piston on the indoor coil. So that's important to kind of remember that. If you have a piston on the indoor coil, you can use the superheat chart. But if it's an expansion valve on the indoor coil, please remember that superheat should be about 10 to 15 with an expansion valve, even though it's on a heat pump in the cooling mode. So let's do some examples together. We see we've got 44 pounds of suction pressure on this heat pump in the cooling mode, R22, about 44 pounds of suction pressure. And we see at that suction pressure, that gives us about 21 degree pressure temperature conversion, about 21 degree pressure temperature conversion. We then, that's step number one. Step number two, we look at the temperature, that vapor line leaving the indoor coil, and we see we've got 59 degrees. Good golly, we've got the difference between 21 and 59. It looks like we have about 38 degrees of superheat. About 38 degrees of superheat. So in this example here, or am I doing my math right? 28 degrees of superheat, excuse me, 28 degrees of superheat. So we've got a very, very high superheat level, and that indoor coil is starved. Well, the person says, well, gee whiz, Joel, it's a heat pump. Well, it doesn't matter. If the superheat is high on the cold coil, that coil is starved for whatever reason. Now remember, team, there's lots of reasons you could have a starved coil. That's not the subject of this training session. You could have a restricted liquid line, a biflow dryer is restricted. There's all different things that could cause this. But we know that we have high superheat, and we're looking for about 10 to 15, but we have very, very high superheat. The indoor coil in this example is starved, and we also have pretty low suction pressure as well, so that would mean something if we were doing refrigeration cycle diagnostics. But step number one, we always want to find the condition of our coils, and in our example, we've got a starved cold coil on this heat pump because its superheat is high. In this second example, we've got an R410A system. We see we're still in the cooling mode of operation. We've got 85 pounds of suction pressure, and that equates to about 24 degrees, about 24 degree pressure temperature conversion at 85 pounds of pressure for a 410A unit. So 24 degrees, step number one, pressure temperature conversion. Step number two, we've got 54 to 55 degrees on our vapor line. So the difference between 24 and 54, that's over 30 degrees. 30 degrees of superheat on that indoor coil. So again, team, we have very, very high superheat. and we've got a starved indoor coil for whatever reason on this heat pump. Remember, team, this whole session about superheat is to find the condition of the coil and determine, is it flooded, is it starved, or is it normal? That becomes a very, very important part of a refrigeration cycle, and again, that'll be a future training session on the whole refrigeration cycle. This is just part of the puzzle right now. Superheat, and what does it mean to the cold coil? Okay, in this next example here, it looks like we have an R22 system, and we've got 82 pounds of suction pressure, 82 pounds of suction pressure on a R22 system. And so that looks like about 49 degrees, about 49 degree pressure temperature conversion. So 82 pounds of pressure, R22 off your chart, your pressure temperature chart, is about 49 degrees. Well, now we measure and we find we have 49 degree, and now we measure the temperature of that cool vapor line off the cold coil. We see we've got a heat pump in the cooling mode, and the temperature of that cool vapor line off that indoor coil is 51 degrees. And we also have a couple degree, about 2 degree difference across the reversing valve. And so that's all giving us some good information there. So 49 degree at 82 pounds of pressure, that equates to 49 degree pressure temperature conversion, step number 1. And then the temperature of the actual cool vapor line is 51 degrees. So the difference between 49 and 51 is only about 2 or 3 degrees of superheat. So in this example, the indoor coil is very flooded. It's extremely flooded for whatever reason. My superheat is low on the indoor coil for whatever reason, and that tells us we have a flooded evaporator, or excuse me, a flooded cold coil on this heat pump. Okay, look at that, team. We've switched modes of operation now. We see that we've got the cold coil is outside in the heating mode of operation, and we've switched modes of operation. We've got hot gas going to the indoor coil, so this tells us we're in the heating mode of operation. And if you take a look at the little arrows, you notice that we've reversed cycle on this heat pump. But hang on a second, that makes no difference. Superheat always applies to the cold coil. So let's take a look at it. We have 88 pounds of suction pressure. This is a 410A unit. At 88 pounds of suction pressure, 88 pounds of suction pressure, looks like we've got about 27 degree pressure temperature conversion, about 27 degrees of pressure temperature conversion. And then we've got about a 36 degree temperature off suction line temperature off of that outdoor coil in the heating mode. So the difference between 27 and 37, or excuse me, the difference between about the difference between about 27 or 20 about 26 to 27 and 36 degrees is about 10 degrees of superheat. So even though this is in the heating mode of operation, if we take a look at our chart, we see that we've got about 10 degrees of superheat, 9 to 10 degrees of superheat. So we would consider that a normal operation, even though it's in the heating mode. The outdoor coil is the evaporator of the cold coil in the heating mode. We still have about 10 degrees of superheat. We consider that a normal condition, even in the heating mode. And we've switched back again, just for another example, into the cooling mode of operation. You'll notice we have a 410A unit in the cooling mode of operation. And so step number 1 for R410A at 121 pounds of suction pressure, 121 pounds of suction pressure. If you take a look at your pressure temperature chart for R410A, 121 pounds of suction pressure gives us about a 41 degree pressure temperature conversion, step number 1, and 52 degrees on the suction line temperature leaving the indoor coil in the cooling mode. So that gives us about 11 degrees of superheat in the cooling mode in this example. So that's about normal with an expansion valve. So remember, team, about 10 to 15 degrees with an expansion valve. It doesn't matter if it's on the indoor coil, the outdoor coil of a heat pump. It doesn't matter if it's just on a straight air conditioning system in the evaporator coil. Now, team, please remember one more time, this is presuming you've got clean coils and you've got a clean air filter on the indoor unit. And when you're taking these measurements, you let the unit run a while and just settle down. One final note before we continue and start winding up our training for today, our recorded session for today. Please remember, team, and put this in your head now, that when we design a duct system, we want to make sure and provide 400 CFM per ton of cooling across that indoor coil for proper operation. 400 CFM per ton of cooling. So if I've got a 2-ton unit sitting outside, I've got a 2-ton system, I need 800 CFM of airflow across that indoor coil for proper operation. If I have a 3-ton unit setting outside, I need 1,200 CFM across that indoor coil on a 3-ton unit for proper operation. So it's very, very important that we have proper airflow and clean coils and a clean indoor air filter. Otherwise, all the superheat measurements and stuff we're doing will be for nothing. We have to have clean coils first and proper airflow first before any of this superheat from a diagnostic standpoint makes any sense. Okay, so here we have another 410A unit. It's 152 pounds of suction pressure. 152 pounds of suction pressure, that gives us about 54-degree pressure temperature conversion. And we see that we've got 55-degree temperature on the vapor line. So the difference between 54 pressure temperature conversion, step number 1, and step number 2, the temperature of the vapor line, it's only about 1 degree of superheat. So that's very, very low. And we see we've got an expansion valve, a Bioflow TXV on the indoor coil. So for whatever reason, that expansion valve is just wide open, and it's feeding a lot of refrigerant into that indoor coil for whatever reason. And there's lots of reasons. Again, we'll get into that at another time on in a refrigeration cycle training session. But in this example, we've got low superheat, a very, very low superheat, only 1 degree of superheat, and we have a flooded indoor coil in this example. Okay, team, at this time we would normally do questions and answers, but because it is a recorded session, we're going to go ahead and conclude this recorded session. This session will be available on the Adobe Connect link that we'll be sending out shortly, and the name of it will be Winsupply Training Overview Superheat. So this time we would like to thank you for your attendance. Thank you for listening to our recorded session, and by all means, please attend our live sessions as well. And we thank you for that opportunity. Be healthy, be safe, and have a great day.